All right, so here we are again. So, under the circumstances, I thought it'd be wise to stay home because and still am, coughing my head off, and sneezing, the whole nine yards. So, rather than give you something, we're going to do it this way today. I'm pretty sure I'll be ready by Thursday, but I did get an email yesterday from the school, and I guess they're kind of nervous about us coming back from spring break. So, as far as I know, they're going to make us wear masks again for another week or so. Um, I'm sure I could not have breathed with a mask on the way I feel right now. So this works out very well. So we can just have our nice online session from our homes and go through the material. And we'll just pick it up where we left off before the spring break, which I hope you had a nice one. Now I was going to bring the exams with me today. And so because I couldn't do that, what I've done instead is I put a couple of columns in the grade book. You should be able to see in your Moodle account where I put the grades. The first midterm, wasn't really necessary because you already have them back. But the second one, I've added as well, so that now you've got them both in there. You should be able to see both exam scores. And then when I hand them back, you'll be able to see what exactly happened, what questions you got right, what questions you got wrong. And then there's one or two people where unfortunately your exam is still sitting in my inbox, my physical mailbox at school, because of course during the break I wasn't over there. And so you'll know, because when you see that your grade is a blank, it means that's the reason that I was not able to physically access it. But I will take care of that later this week. All right. In the meantime, we're in the middle of chapter 11 now. And so far what we've done is we've spent a great deal of time looking at the science of counting, which is also known as combinatorics. You might recall we introduced factorial as an operator that allows us to calculate how many ways n objects can be arranged, like the cars in a garage, for example. That was kind of fun. Or the number of posters on the wall. How many different ways can we hang our posters? So it turned out that can be easily calculated with this operator factorial. Let's jump ahead and find, there it is. And that, of course, is on your phone calculator. If you look, let me go find it right now. You should be able to find it. Where is it? It's way down in the bottom left-hand corner. It's almost exactly the bottom left. It's just above that button that lets you switch between radians and degrees. And it's right next to the sign button, X factorial, and that will take care of any factorial that you need. So we did several examples of this. And then we introduced two more complicated concepts, combinations and permutations, where with permutations, we're choosing a collection of objects from a larger group in such a way that the order matters, the order of selection matters. Like with choosing students to fill the officers of a club, the order in which I select them makes a difference, because in this first case, for example, student 3 is the president, 1 is the vice president, 7 is the treasurer. Here, 7 is the president, 3 is the vice president, and 1 is the treasurer. So the order does matter in this case. So each choice that I have of 3 students out of 10 is known as a permutation. And so the question is, how many are there? How many different permutations are possible? So we have this formula, which you can implement yourself because your calculators have the factorial button. And you can see in this case, it turned out to be 720, because that would be equal to 10 factorial over 7 factorial, or 720. If you have a more advanced calculator like the Texas Instrument series, it most likely has this button already built into it. So you don't even have to plug numbers into the formula. But if you don't, that's fine. You can do it this way. And then we also introduced the concept of combinations, where we saw that the order of selection does not matter. And so, for example, we looked at the case of toppings. We're choosing ice cream toppings at Haagen-Dazs. And we were assuming that you were given the choice of any 2 out of 5 for $1. And so since the order of selection does not matter, the number of possibilities is quite a bit smaller than with permutations. And in fact, here, we only had 10. And so there's a formula for that too. Just jump ahead and show it to you. Here it is. So with the combinations, what we've done is we've added this extra term in the denominator, r factorial, because what that does is it strips out the effect of repeated choices with the same numbers. And so here with the Haagen-Dazs, we're able to prove mathematically that the number of choices is in fact 10. Okay, it's, writing them out is fine, but it's very impractical. At some point, it's much easier to simply use the formula. All right, now, all that being said, we're now ready for probability theory itself, which is what we've been building up to. And when that's done, maybe probably not today, but when that's finally done, we'll be ready for chapter 12, which is an introduction to statistics. And the reason why they're taught in this order is because probability theory is the foundation for all of statistics. And then we're done. We're done with the course. And so the final exam will be exclusively on chapters 11 and 12. You'll be happy to hear. And we'll review, of course, we'll have problem sets for chapters 11 and 12, et cetera, et cetera. And so at some point we have to sit down and figure out a schedule. I'm going to say that we'll almost certainly have time to get our final done before the actual final exam week, because for whatever reason, we've gone through the material a little faster than was absolutely necessary. You never know, every semester is different. Sometimes the pacing is just different. Every group, officially, good question. As far as I know, in fact, why don't we do this? Because I know people are trying to make plans and I'm trying to help you here, but I just want to mention right up front that if there's truly important conflict on your schedule, let's say we randomly pick May the 10th for our test and you just can't be there, it's possible for us to separately give you the test at a different time. So in other words, nobody will be inconvenienced no matter what date we pick. If you have a genuine conflict that prevents you from being there that day, we can always give you the test at an earlier or a later time. Okay, so you don't really have to worry about that, but it still would be nice if we could just get it all done and get it out of the way. So yeah, that happens all the time. I mean, people have to be places, they have to fly somewhere. One year we had somebody who's had signed his contract to be in a movie in South Africa, and he had to catch his plane. And I gave it to him sooner so he could get out of there on time. And then sadly enough, the movie got canceled, but he got his test out of the way. Here it is. So for us, the last, oh man, where is it? Here we go. Okay, where are we? Right here. So it says here, Monday the 16th is our official date. Now, here's how I'm going to work this. And this is what I've done in the past. We should have no trouble finishing in time. Let's look at the calendar. That's here. Okay, so there you go. So I'm thinking now the week of the 9th, we probably should be able to get it done, let's say Monday the 9th. I think the timing is such that we could probably finish it by then. But then having said that, if anyone really wants to take it on the 16th, I will make that option available to you. Because, some people might want the extra time to study. If you really can't be there on the 9th, let's say, it turns out to be the 9th, like I said, we can switch it around to fit your schedule. So, it doesn't need to be a problem for anyone, but I think that we can probably have it done by then because, like I said, we're a little ahead of schedule right now. And the 9th is quite a ways off. I mean, it's only the 18th right now. What does that give us? The week of the 18th, 25th, and that's 3 weeks. That's still 3 weeks. That's a long time. So I don't see why we shouldn't be able to get it done on the 9th during our normal class time, and then we'll be done. But having said that, we may have to adjust it slightly, but I think we certainly can give it a shot. Let me just write this down somewhere. But officially, it's meant to be done on the 16th. Okay. Now I've got another section of this class. Let's see when they have theirs. My other section, oh my God, the 19th. Wow, that's a long ways off. I guess nobody's going to want to switch. And I also, okay. I also have pre-calculus on Wednesdays. Their exam is scheduled for the 18th. That doesn't help you, but in that case, in that class, I am actually going to give it to them not on the 18th, but on the 11th. So if you want to, if there's some reason why the 11th works better for you, and just make a note of this. It's 3 o'clock in the afternoon, though. I just want to point that out. The pre-calc is 3 o'clock in the afternoon on Wednesdays. So while they're officially scheduled for Wednesday the 18th, I'm going to give it to them on Wednesday the 11th at 3 o'clock in the afternoon. So if there's a conflict in your schedule, but you can come on Wednesday the 11th, that would be okay too. Yeah, it might be a good idea. All right, so we'll figure that out. Ooh, sorry about that. Oh my God. Oh man. Well, that was nasty, but there doesn't seem to be a button here that can push when I'm about to sneeze, so I'll just have to be careful. Anyway, let's get back to it. Okay, here we go. So probability theory, yes. So this is what we've been building up to. Probability theory is what this is all about. And what we're trying to do is develop or establish a mathematical framework of some kind based on the concept of uncertainty. Now, of course, as you know, there's a lot of uncertainty in the real world. We don't know what's going to happen tomorrow. We don't know what the weather's going to be like. Although, you know, weather forecasting is getting better, it's still a tricky thing to do properly. In other words, the weather forecasts, at least a day or two in advance, are usually pretty good. If you start looking further into the future, they start to get less and less reliable because so many different factors are involved with forecasting the weather. And the least little thing can change it up pretty considerably. Like yesterday, I don't know if you noticed it, but there was actually snowflakes yesterday on Easter. Who would have thought that, you know? So here, what we're trying to do, though, is essentially establish a mathematical framework so that even if we don't know what's coming, we can at least assess probabilities of different things happening. I might want to know, for example, what's the likelihood that the Dow Jones goes up by 100 points this week? Or I might want to know the probability that Apple stock goes up 50% or something, you know, over the next month. There's all kinds of things I might want to calculate probabilities for. And so this will enable us to do that. So we're going to start with the concept of the random experiment. And this is an experiment, or it's a process, I should say, that generates outcomes in such a way that all possible outcomes are known in advance, but the actual outcome is not going to be known in advance. Otherwise, it's not random. Okay, if we already know what's going to happen, it is no longer considered to be random. And that doesn't help us here. We're just trying to figure out what could happen and what's the likelihood of different outcomes actually happening. Now, there's a million different ways we can have a random experiment. As it turns out, games of chance could all be considered random experiment. For example, spinning a roulette wheel. A roulette wheel, if you've never seen one, is something you find in a casino. You see that on, you know, like James Bond movies sometimes. What's happening is that there's a big wheel being spun. In his case, it's in a very fancy casino where everyone's wearing tuxedos, and they're betting tons of money on each spin. And so it's just a big wheel, and you can see what's going to happen is the ball bounces around and it lands in front of one of these numbers. And so we don't know which one will turn up. If we did, we could make a lot of money, that's for sure. But we do know what could happen. And we do know also what's the probability of each one of these numbers turning up because they're all equally likely. So a standard roulette wheel in the US at least has the numbers 1 through 36. And among the first 36 numbers, all of these are either red or black. And then they have, usually in the US at least, two more 0 and 00, which are green. European casinos tend to have just the 0. But here in the US, it's 0 and 00. So you can place bets on any of these numbers individually, or ranges of numbers, or colors, evens and odds, things like that. There's all kinds of possibilities. And so what happens, of course, if the ball lands in your number, you win. And the amount you win depends on what bet you placed. But again, the whole idea here is that we don't know up front what will happen, but we do know what could happen. And each number on that wheel is equally likely to turn up. The wheel is constructed to make sure that they're all equally likely. So the probability of any number would, of course, be 1 out of 38. Because there's 38 equally likely numbers. So you can, yes, you can. Well, in fact, this one, if you look in Moodle, the last time we met on the 7th, oh, I thought Moodle was still open. It's, if you notice, it's the chapter 11 notes that are just the ones that I started out with, the blank ones, so to speak, along with these. Wait a minute. I thought I had Moodle still open here. Oh, for Christ's sake, I've got so much stuff open. Who knows where anything is. Let me just go show it to you. Now, there's all the stuff I'm adding by hand. You'll be able to get at that too, because like the last time I said that we met on the 7th, I did exactly the same thing. You'll see that we have chapter 11, but also chapter 11 with notes 4, 7, 22 means that those are the handwritten notes that I did on the 11th when we recorded this session. And that's one of the good things about this that you don't get in the classroom. Basically, everything I write on the board disappears. Unless you take a picture of it or copy it down, it's just gone. Whereas here, it's forever. As soon as I write on the slides, I can hang on to this forever. And so I will make these available to you. The date, I've changed the date to today's date. And so, yes, you'll have you will be able to get your hands on this. All right, anyway, so a deck of cards. Everyone knows that a standard deck of cards is 52 cards. And when I pick a card from a deck, each one is equally likely to be chosen. So if I wanted to know, let's say, the probability of picking the ace of spades, it's just 1 out of 52. Or if I want to know the probability of getting a red card, that would be 26 out of 52 because half the cards are red and half are black. And of course, everybody has played games with dice. Everybody knows how they work. Each die has 1 to 6 on it. Therefore, when you roll 2 dice, the range of possibilities is from 2 to 12, although each one is not equally likely to occur, as it turns out. For example, you're much more likely to get a 7 than, let's say, an 11. The number of possibilities depends on the dice. Just turn this down. So, and we could go through and figure that out if you wanted to. But what we're going to do instead is we're going to keep this simple. We're going to use an experiment where we're rolling a die twice, but whenever we roll it, we're only focused on evens and odds. In other words, imagine we're playing some game in the casino where the prize that we win depends not on the actual number that we roll, but whether it's even or odd. So if that's the case, if I roll the die twice and I'm only paying attention to evens and odds, then there's only really 4 things that can happen. I can get an even number followed by another even, an even followed by an odd followed by an even, and an odd followed by an odd. Okay, now, because of the way the dice are set up, each die has exactly 3 evens and 3 odds. So that means getting an even or an odd, it has the same probability, which is 1/2 when I roll the die once. When I roll the die twice, these 4 possibilities are all equally likely to occur. Now, if you want to go through and prove it, you can. You can make up a list of all 36 possible outcomes and you write down which ones fall into each of these 4 categories. And you'd find that there are 9 cases with even followed by even, 9 cases with even followed by odd, 9 cases with odd followed by even, and 9 cases where there's odd followed by odd. In other words, 9 out of 36 or 1/4. So you got 4 equally likely outcomes. And by the way, just for a fun side note, the word dice is plural. We tend to call them dice, whether there's one or more. the singular is die, a single die. You roll it once, it's a die. If you roll two dice, it's dice. Okay, so the plural is dice. Okay, well, anyway, so what's going to happen here is that every time we roll the die, we're going to double the number of possible outcomes. Let's see. Actually, I'll tell you what, let's do this for a second. I just want to demonstrate what I was just telling you about, how to figure out that all these outcomes are equally likely. What we could do is build a little chart in Excel. And, you know, for example, I could have a pair of ones. Okay. So what I'm going to do is very quickly run through all the possible outcomes of rolling the die twice, or rolling a pair of dice. So you can see what's happening. In each case, I've got a pair of numbers. The first one represents what happens on the first die or the first roll. And the second one is, of course, the second one. And we're going to discover that there's 36 possible outcomes. Oops. So what I'd like to do is just categorize them. So all the cases where we have an odd followed by an odd, let's make those yellow. Oh, this will be easy. So odd followed by odd is yellow. Okay, good. Now, how about odd followed by even? Let's make that green. What the heck? Green. Not just any green. Let's make it this color. So these are odd followed by even. Oh, I think this is kind of fun. And by the way, each of those 36 outcomes is equally likely. That has to be understood right up front because each die has 6 outcomes. And the die are structured to make sure that each side is equally likely to turn up. So you've got 36 actual outcomes that could happen when you roll a pair of dice, each of which is equally likely. So let's look for even followed by odd. I guess we can make that blue. No, it's too close to the other one. Oh boy. No blue then. How about some kind of purple? Oh, that's better. Okay. Even followed by odd would be this one. And then we need to find the cases where we have even followed by even. And let's just pick, I don't know, how about orange? Some shade of orange that's very easy to distinguish from the others. Okay, that should do it. Even. Oops, I missed one. All right, so how many are there? There's 9 of each. If you go through and count them all, you'll see that there's 9 for each color. And so 9 out of 36. So the probability of each of these outcomes has a probability of 9 out of 36, which is just 1/4. or 0.25, of course. And so that's why that's correct. Yes. So the one, yeah, odd is 1, 3, 5, 7, 9, et cetera, et cetera. Even is 2, 4, 6, 8, 10, et cetera, et cetera. The ones that are divisible by 2 are even. Let's put it that way. Anyway, so this little chart is just proof that what we're saying here is that all of these are equally likely. Now, if I roll the die a third time, let's say instead of some games, you do need 3 dice. What's going to happen is that the number of outcomes will increase very, very dramatically. And if we did that, we would need to have odd, 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 odd. Even the number of possibilities is also much higher. It's going to grow very quickly. So in order to keep things simple, instead of focusing on these actual numbers, we're going to focus on evens and odds. Okay, now, if that happens, this little diagram is meant to indicate this is a graph that makes it possible for you to see visually what happens every time we increase the number of rolls of the die. It's called a binary tree. And you can see that after you roll the die once, there's only 2 things that can happen, even or odd. And each one has a probability of 1/2. If I roll the die a second time, as we've just seen, there's 4 possibilities, each of which is equally likely, which means 1/4. But if I roll the die a third time, all of a sudden I've got 8 possibilities, and each one now has a probability, therefore, of 1/8. So this diagram makes it possible to keep track of all the outcomes that can take place when you roll the die. If I did it again, there'd be 16 possibilities. So each time I roll the die, let me just note that here. Let's see. Each time the die is rolled, the number of possible outcomes doubles. Okay, so with 2 rolls, 4 outcomes. 1 roll is 2 outcomes. 2 is 4. As we've seen, 3 rolls is 8 outcomes rather. 4 rolls is 16 outcomes. And it goes on and on and on. And each one, when we're thinking only in terms of odds and evens, each one is equally likely to occur. And if you don't believe it, you can make up a chart like I did here in Excel, and you can just look at them and you'll say, oh yeah, it does work that way. And that's because each die has the same number of even and odd numbers on it. All right. Now, by the way, there do exist die that don't look like this at all. In fact, one year I remember we went onto the internet and we found that there's all kinds of weird dice out there that you can buy. In fact, you can actually buy, believe it or not, a die that has 100 sides on it. Look at this thing. Yeah, when you roll it, there's 1 out of 100 possibilities that it can turn up. It's pretty interesting. I don't know what kind of game would require that, but there it is. Look at that, 100. There's all kinds of possibilities here. You never know what you're going to find on the internet. But, you know, there's others, like, let's say you need a 16-sided die or something like that. Yeah, I mean, it's a little bit more down to earth. But there might be a game, like here, according to this, it's the dark blue glass D&D dice set dragon dice. So apparently there's a game that requires a 16-sided die. Well, there you go. If you want one, it will cost you $18. Pretty cool, I must say. Look at that. You might want to buy a pair of these just because they look so cool. Look at that. I guess the 16th side is the dragon. That's what I'm guessing. But the way they've had to cut it so that each side is equally likely to turn up. Okay, but in principle, you can have any number of sides that you want. I guess as long as it's even. I don't think you can make a die that has an odd number of sides. But what do I know about making dice? But anyway, all right, let's get back to this. So now we're going to gather up all of our outcomes into a very special type of set, which is called the sample space. Now, a set, as you remember, is simply a collection of objects. The order in which we list the objects is not relevant. And so those little, these symbols, the braces, are meant to indicate this is a set. And it's simply a collection of objects, like I said, where the order doesn't mean anything. I just happened to choose this order. I could have had 00 first, for example. And this set will help us define all the probabilities of all the events that can occur when I conduct this experiment. Okay. So S means the sample space, and then EE means even followed by even. EO is even followed by odd. OE is odd followed by even, and OO is odd followed by odd. So every experiment will have a sample space. That's the starting point. Once we have that in place, we can then establish probabilities. Okay. All right. Now, just a quick review of set operations or set algebra, in case you've started to forget. It's been a long time, I'm guessing, since you were introduced to sets, but you were certainly introduced to them somewhere along the way. And you might remember, hold on one second, that union, this U is the union operator, and it means if I want, for example, here the union of A and B, all I'm doing is taking sets A and B and combining them into a new set that contains all of the elements that are in A or B or possibly both. So since set A contains 1, 2, and 3, set B contains 2, 3, and 4, when I bring them together, I end up with 1, 2, 3, and 4. That's my union. All right. So sometimes in some textbooks, they use the English word or instead of union. So you may have seen that. Now, what other set operations did you learn? The upside down U is called intersection. And this means I'm creating a new set which contains only the elements that are common to the two sets. Here, for example, A and B, the only element they have in common is 2. So the intersection between A and B is the set containing the element 2, because that's the only element they have in common. And sometimes you see the word the English word and used instead of intersection. All right. Now, sometimes when we calculate an intersection, for example, here between A and C, they have no elements in common. So we say that their intersection is the empty set, which either is shown by the brackets with no elements, or sometimes you see the 0 with a slash through it. It means the same thing. And in this case, because A and C have no elements in common, they're said to be mutually exclusive. All right, mutually exclusive simply means we have two sets that have nothing in common. So that happens. You know, unions are different. You're just combining them. Here with an intersection, you're looking for what do they have in common, if anything. And the answer is they may not have anything, which in this case, they do not. And you can see the same thing would hold true for A and D. Oh, sorry, not A and D, C and D. C and D also have nothing in common. They would therefore be considered to be mutually exclusive. Now, this is the one we really are focused on right now. Subset, that little sideways C, as it looks like a little C, but it's actually the symbol for subset. A subset means that one set is completely contained within another. So here, D is a subset of A because all the elements in D are also elements in A. And so therefore we say that D is a subset of A. All right, now, of course, not all sets are subsets of each other. You can see very clearly that D is not a subset of C. C is not a subset of either A, B, or D. Okay, because it has nothing in common with them. But, you can make up real world examples of this very easily. For example, the set of all dance majors at SUNY Purchase is a subset of the entire student body. Okay. In other words, the dance majors are also SUNY Purchase students. Therefore, they are a subset of the entire student body. Oh, here I chose, all right, art majors, whatever. B is a subset of A. B is all the art majors at SUNY Purchase, and A is all the SUNY Purchase students. Therefore, B is a subset of A because all the art majors at SUNY Purchase are also SUNY Purchase majors, students rather. Okay. Now, the symbol for not being a subset is very simply the symbol for subset with a slash through it. So C is not a subset of D because the 5 is not contained in set D. There's no 5 in there. All right, so I think that's all we need to review as far as sets are concerned. But remember, all of probability theory is based on set theory. That's why we need to do this. We're going to define a very important idea here, the notion of the event. And an event is a subset of the sample space. And we can define any event that we like. And the purpose of doing this is so that we can calculate its probability. Let's say, for example, I'm playing a game in the casino where I can win a prize if I get either EO, OE, or OO. So we'll call that the event that at most one even number turns up. Okay, I lose if I get 2 even numbers. I win if I get 1 or no evens. So F is defined as an event because it is itself a set of outcomes which are part of the sample space. Now, what am I supposed to do with F? How do I calculate its probability? Well, there's a couple of things I can do. All right. Well, first of all, we already have seen that each of these events, EE, EO, OE, and OO, are equally likely to occur. In fact, we've already seen from my spreadsheet that each one of these, this OO, of course, this is what we mean by OO. Let's do this. Let's make this a little more comprehensive. Just so it's clear that they mean the same thing. Okay, so each one of these, as we've already seen, has the same probability. So in other words, I can make the case that POO is 0.25 or 1/4. Okay. All right, that takes care of that. Now, before I lose this, let me save this. You might want to look at this later on. I'm going to save this. Okay, I'll post this on Blackboard, Moodle later on, in case you want to look at it again. So if that's the case, each of these separately has a probability of 1/4. So if that's the case, then it stands to reason that the probability of F is 1/4 plus 1/4 plus 1/4, which is 3/4 or 0.75, because I'm simply adding them up. All right, so if each of these outcomes has a probability of 1/4, the probability of any one of them happening is 3/4. Okay, I literally just add them up. And that's all I have to do. It's that straightforward. You see that? It's not hard at all. You just take the individual probabilities and add them up, and you're all set. Now, because they're all equally likely, which isn't always true, we'll see examples where this is not true. This approach always works, but when they are all equally likely, we can speed it up just a little bit by noting that we have 3 outcomes, each with a probability of 1/4. So what I can do is rewrite it in the following way, but this is optional. I can rewrite the probability of any given event E is the number of events in E divided by the number of events or elements in the sample space, but only when they're all equally likely to occur. Okay, so in this case, we would just say 3/4. That's it. And we're done. Okay. So let's do another example of this. What if we did roll the die 3 times? Let's see. Well, I don't think we don't want to make a chart, because the chart would then require, here we've only got 36 possibilities. Rolling the die a third time requires 216 possibilities. So I'm not going to make a separate chart for that, but based on the same logic, we've got 8 outcomes then, each of which is equally likely. So in other words, you can see all of a sudden there's 8 possibilities. And so what I've done here is I've organized them in a specific way. I've got 3 evens, and then here I have a group of 3 outcomes, each of which has 2 evens. Then I've got 3 cases where there's only 1 even, and then I've got the final case where there's no evens at all. So that's how I can break up all 8 possibilities. And so if I wanted to know the probability of getting at least 2 evens, what I'm basically looking for is all the cases where I have either 2 E's or 3. And if you just go through and count them, you'll see that that means there's 4 ways that can happen out of 8 equally likely outcomes. And so I end up with 1/2. 4/8 is 1/2. So this one is a little bit more complicated. You can see it's the same logic. 8 possible outcomes, each of which is equally likely. The event A is at least 2 evens. I have to, let's say, get that to win my prize. And how can that happen? There's 4 ways of getting that out of 8 possibilities. Since we know in advance that all outcomes are equally likely, I just have to count 4 elements in A and divide by 8 for the entire sample space. I could have also added up the individual probabilities, and then I would have ended up with 4 outcomes, each with a probability of an 8, which adds up to 4/8. All right. So far, so good, I hope. Here's an interesting one. Suppose we were playing a game with a special pair of dice. Now this time, the dice, for whatever reason, have 2 even numbers and 4 odds. Now this is very different, because then the probabilities are not equal to each other. Okay, in other words, there's still 4 possible outcomes. EE, EO, OE, and OO, but each one is not equally likely to occur, because the dice themselves have different numbers of values. Let's say each die has the numbers. How would that work? For some bizarre reason, it doesn't have a 6. Okay, so there's 2 evens. And 4 odds. 1, 3, 5, 7. So now the probability of getting an even is 2 out of 6. And the probability of getting an odd is now 4 out of 6. So that's going to change not the sample space, but the probabilities of getting these outcomes. In fact, I've got a chart on the next page where you can see what the new probabilities are. Yeah, this is some game they just invented at the casino. The We Don't Like 6 game. So anyway, yeah, you can see in the top, E and O now have 2 different probabilities, 1/3 and 2/3. And you can see down here, we can use that information to come up with the likelihood of each of these outcomes. In other words, E is now 1/9. EO is now 2/9. OE is 2/9, and OO is 4/9. Why? Because when you multiply the probability of getting an even by itself, you'll get EE. E times O is 1/3 times 2/3. O times E, 2/9. And then OO is 2/3 times 2/3, which is 4/9. So these are no longer equally likely to occur. So what we're going to do now is recalculate the probability of F, which means at most 1 even. All right, let me give you a minute to catch up here. Okay, now what happens with this F? How do we figure it out now? Well, this time we're just going to add up the individual probabilities. So let's see how that would work out. Okay, so this time EO, as you can see from the previous page, is 2/9. The probability of OE is 2/9. The probability of OO is 4/9. So by adding them up, this time instead of getting 3/4, I get 8/9. And if you notice, I cannot, the formula N number in F over the number in S does not work in this case, because the outcomes are not equally likely. So instead, you just add up the individual probabilities. The probability of EO plus OE plus OO adds up to 8/9. All right. So you could come up with a lot of possible examples, and they'd all be fun, but the basic logic never changes. Okay, which is good. We don't like it if the logic changes. So anyway, with all that being said, we can now introduce what are the so-called rules of probability. Now, the rules of probability are designed to help us with more complex situations. So you can see there's 3 of them: the addition rule, the complement rule, the multiplication rule. The first 2 are very, very straightforward. The third one is a bit messier, and we'll need to do a little more background before we introduce it. But for now, we can start with these 2. And these involve, the first one involves unions. So we already know what a union is. It's a combination of 2 sets. The complement rule, we will have to explain what the word complement means in this case. And the multiplication rule is meant for intersections. Okay, so we'll see that as we go along. All right, so I'm going to show you the addition rule. And it's not that complicated. What it says is that if you want to calculate the probability of a union of 2 events, You have to add up the probabilities of the individual events, and then you're going to subtract the intersection between them. So I'm going to show you in a second why you need to do that. All right, so this is our addition rule, and you can see it involves unions and intersections. Oh, yes. So I'm going to draw a picture. And when you see this, you're probably going to say, oh my God, I haven't seen one of those in ages. All right, let me show you a picture that will help us understand why the rule is set up the way it is. This type of diagram, as you may remember, is called a Venn diagram. They're perfectly suited for illustrating the relationships between sets. So obviously, so A is set A, B is set B, and the shaded area is their intersection. The union of these two is everything that is in A or B or both. Now, here's the thing. If I just add up A and B and let it go with that, like let's say I don't have this intersection subtracted here, I would count the shaded region twice. So in order to offset that, I need to subtract that area so they end up only counting these three pieces. In other words, think of this as section 1. So in other words, by writing it like that, you could see that the union, we want it to be 1 plus 2 plus 3. Actually, let me put this on a new slide here. So actually, let's see if I can fit this all in here. Oh no, I thought it would grab the whole thing. Oh, this is so bad. All right. Oh, for God's sakes, I'll just draw another one. So in other words, the union is 1 plus 2 plus 3. A is 1 plus 2. B is 2 plus 3. And then we subtract off just 2. And so you can see where they double count the 2's, we subtract that off. So we end up with what we need, which is 1 plus 2 plus 3. So that's why we need to do it this way. Let me just clean this up a little. There, that's easier to see it. Okay, so that's why we have to subtract the intersection, because otherwise we would be counting section 2 twice. All right, let's see some examples. So we're going to go back to the same experiment we had before. We roll the die. Now we're back, by the way, to the case where they're all equally likely. This is the normal die, basically. Forget that other example. We're back to normal dice. E, E, O, O, E, O, O. They're all equally likely. And so we're defining the event A to be the first roll is even, and B is the event that the first, exactly one roll is odd. So with all these cases, what you want to do is write up a list of all the elements that belong to those sets. Okay, so in other words, this one means EE and EO, because those are the cases where the first roll is even. Exactly one roll is odd means EO and OE. So think of these events as simply sets, which is what they are. They're sets, subsets of the sample space. So once you define that, it's easy to calculate what you're looking for. So what we're going to do now is ask the following question. What is the probability that the first roll is even or exactly one roll is odd? So in other words, this is the same thing as saying, what's the probability of A union B? Because remember, union and or mean the same thing. So in other words, it's saying use the addition rule to figure this out. Now, we know that the addition rule requires us to know the probability of A and B, but we also have to know the probability of their intersection. Well, in order to do that, we have to know what their intersection is. So if you look at these two carefully, you'll see that they only have one element in common. EO. Okay, so that tells me that the intersection between A and B consists of the single element EO. We're going to need that to do our calculations. In fact, I've summarized everything right here. There's A and B, and there's our intersection. Okay, and again, it's because these overlap by one element. All right, well, if that's the case, now remember, each of these outcomes is equally likely to occur. Oh, so what does that tell me? This probability is 2 out of 4, or sorry, yes, 2 out of 4 or a half. This one is 2 out of 4. And this one is 1 out of 4. So now all I have to do is plug these into the addition rule, and I'm all set. Okay. You can see it's nice that we can assume that all the outcomes are equally likely. Very nice. All right, let's plug them in, and you can see the final result is 3/4. Now, it turns out that in a simple case like this, there's another thing we could have done, and it would have meant not needing the addition rule at all. Okay, so here's what I could have done. I could have just figured out for myself what elements belong to that union. So for example, let's go get this information back. Oh, what happened? There we go. If that's the case, then the union, as it shows right here, is EE, EO, and OE. It has three elements in it, all of which are equally likely to occur. So all I would have had to do is say, oh, if that's the case, the probability is the number of elements in that union. Whoops, I chose one. The number of events is 3 that qualify in that union. Is the number of elements in the union over the number of events in the sample space, and you would have gotten the same result. So either way would work. Now, as you get to more complicated situations, though, you're probably better off just using the rule. Okay, but I just wanted you to see that it is often possible to do the same thing in multiple ways. All right. But here, because it was straightforward, we could have done it either way. Sometimes, though, you'll see cases where you've got probabilities, but if you don't know what the original sample space was or how these outcomes were generated, then you really have to use the rule. But sometimes it's possible to do it more than one way. All right, now, what about cases where the events are mutually exclusive? Sometimes, by the way, the word disjoint means the same thing as mutually exclusive. What happens to the addition rule in that case? Well, let me just point out something very important. The empty set means there's nothing in that set, okay? A intersect B is empty when they're mutually exclusive. And that, as we've seen, is the empty set. There's nothing in there. So suppose, for example, A represents the odd numbers and B is the even numbers. They don't overlap at all. They are said to be mutually exclusive. Okay, so that being the case, it turns out the probability of the empty set is 0 by definition. Okay, so just keep that in mind. The probability of the empty set is 0. And while we're at it, I just want to point out that the probability of the entire sample space is 1. So that empty set has a probability of 0. So if A and B are mutually exclusive, meaning they have nothing in common, the probability of their intersection is also 0. Now, what does that have to do with the addition rule? Well, let's see what happens now. It turns out that we can simplify that rule a little bit because we don't need to subtract the intersection. Why do we? Because it's the original rule was this. So you can see when A and B are mutually exclusive, then this probability is 0, and that leaves us to this. And now the probability of this union is just the sum of these two individual probabilities. Okay, so we call this the simplified addition rule. All right. So let's look at a case where we can actually use this thing. Okay, so we'll go back to the same die rolling experiment. And we're going to note that, let's say A represents the event that the first roll is even, and this B is the event that the first roll is odd. Now you can clearly see logically that those are mutually exclusive events because the first roll can't be both even and odd. So we're going to be able to use the simplified addition rule in this case. Well, first things first, let's identify what elements belong to A and B. Let me just copy these to the next slide. So therefore, A contains the elements EE and EO. B contains the elements OE and OO. Since there's two equally likely outcomes in each of these sets, the probabilities are, in both cases, either 2/4 or 1/2. All right, the intersection, which we already know is empty. Therefore, it has a probability of 0. So what I'm going to do is plug these numbers into the simple or simplified addition rule. When I ask the following question, what is the probability that the first roll is even or odd? Which means the probability of the union. So again, we already know that we can use the simplified addition rule. So let's figure it out. What is it? Well, it's so simple. Add them up, and we end up with 1/2 plus 1/2 is 1. End of story. And you can see why. Now, by the way, when the probability is 1, indicates what's called a certain event, something that must happen. So you can see why that applies here, because the first roll has to be either even or odd. There are no other options. So that's why their union is 1, has a probability 1, because what we're saying is that either the first roll will be even or it will be odd with certainty. So therefore, it makes sense that the sum of their probabilities is 1, because that's guaranteed to happen. Wow. So far, so good, I hope. This is pretty interesting stuff, isn't it? Yes, very interesting. Okay. Now, what about the complement rule, which we saw earlier? Remember in the list, there's 3 rules that we want to see here. The addition rule, of course, now we know represents the probability of the union. The complement rule, well, that requires us to define what we mean by complements. Very good. So let's do that right now. 2 events. Now, here's the formal definition. We're going to go through and see some examples. The formal definition of complements is this. The probability of A is 1/2 because A is the event that we either get EO or OE, and B is the event that we get the first roll is odd. And since they're all equally likely, this equals, oops, I have drawn this incorrectly. Hold on. Yeah, that's where it's coming from, because there's two events that are contained in A, and the same thing with B. And since they're equally likely, that means each one must be a half, or two quarters, actually. So when I add them up, I get one. Anyway, so the I'm going to show you the formal definition of complements, and it looks scary and all, but when I tell you what they mean, it'll make a lot more sense. Okay, so we'll use some fun examples. All right, so formally, for two events to be complements, it must be true that number one, their union is the entire sample space, and number two, they are mutually exclusive. Okay, mutually exclusive, they have no elements in common, but their union is the entire sample space. So let me show you an example of this before we go any further. Okay, so the union is S, the intersection is the empty set. Whoops, hold on. Okay, a card is chosen from a deck. A represents the event that the card is red, and B is the event the card is black. Are A and B complements? Good question. Are they complements? Well, in order to demonstrate that they're complements, well, they are, but let's see why. They have to satisfy those two requirements. Okay, which let me go copy these from up here. Okay, let's do something different here. In order for A and B to be complements, it must be true that, okay, so I'll just go grab them. Now, is it true that their union is the entire, oh, and by the way, in this case, let me just mention it up here. Note that the sample space is the entire deck in this case. Okay, just want to mention that, make that clear. Is it true that A and B is S? Now, this is the equivalent of saying the union of the red cards and black cards is the entire deck, which we know is true because there are no other cards. They're all either red or black. There's no green, for example. So the union is the entire deck. And here, this means that no cards can be both red and black. And I mean, if you've ever seen a deck of cards, you know that this is true. If you took all the red and blacks and put them together, you'd have the entire deck. But you'll notice that none of the cards can be both red and black. And since both of these conditions are true, that tells us that A and B are in fact complements. Right? Complements. So remember what that means. It's a way of breaking up a set into two pieces where they represent the entire sample space and yet they have nothing in common. So let me show you a couple of others. It's not hard to come up with examples of this. Let's try another one. Suppose that the sample space is the natural numbers. Ooh, that's an interesting one. Remember from way back? 1, 2, 3, 4, ... A is the even numbers. B is the odd numbers. Are A and B complements? Well, let's find out. Well, the answer is yes. You can see why. I mean, once you start to get a feel for this, because A and B obviously do not have any elements in common. And yet all the natural numbers have to be one or the other. There are no exceptions. Okay, so if this is your sample space, every one of those numbers is either even or odd, but none of them are both. Okay, so the answer is yes. And let's do it based on the same reasoning. All natural numbers are either odd or even. That's what this first one means in English. And down here, this indicates that none of the natural numbers are both even and odd. Okay, so that tells me that yes, they're complements. Both of our conditions were satisfied. Okay. So there's others we could do. Like, let me do a quick one here. The white and black pieces on a chessboard are complements because all of the pieces are either white or black. None of the pieces can be both. And that's all it takes. Now, let me show you an example where they're not complements, just so you get a feel for, like, what about this case? Now, this, just as a quick reminder, I want to remind everyone that in a standard deck of cards, there are 4 suits. Among the red cards, 13 are hearts and 13 are diamonds. Among the black cards, 13 are clubs and 13 are spades. All right, so here's what I want to know. Let's just say I pick a card from a deck. A means the card is a heart. B means the card is a diamond. Are these complements? That's a very good question. Well, we're going to see that they're not, and here's why. So in other words, remember the two conditions. The probability of A union B, or sorry, A union B does not equal to the sample space. Let me just grab these. Actually, we'll do that one first. How about that? So while the first condition is actually true, no card is both a heart and a diamond. Actually, so yes, that's right. The problem is with the second one. The union of the hearts and diamonds does not, oh, running out of space here, equal the entire sample space, which means the deck. All right, I'll add this to a new, I'll move this to a new slide. Hold on. Okay, so you can see in this case, the first condition, this condition is true, but the second condition is not true. Therefore, they're not complements. Since both conditions are not true, the A and B are not complements. And that just means you can't use the complement rule on them. You have to try something else. I have to double check and see. I don't know. I haven't looked today. Anyway, so yes, so they're not complements. Now, we're going to introduce some notation here. Just to indicate, there's a special notation we'll use for complements. If it turns out that B is the complement of A, we can often rewrite it instead of B, we can replace it with A with a little c, which is meant to represent a complement. Okay, so when you see that little c, it means that we have A in its own complement. So what I'm going to do, because we're running out of time, I'm just going to show you what the complement rule is, and then we'll do some examples on Thursday. All right, so this is what it looks like. There's actually two ways of expressing the same thing. The probability of A is equal to 1 minus the probability of its complement, or the probability of A complement is equal to 1 minus the probability of A. They both mean the same thing. You can see, and we'll explain how and why this is happening. But for now, I just wanted you to see what this relationship looks like. And then we can take it from there. Okay. All right. So that's good. I guess we'll knock it off right about here. And then I'm pretty sure I'll be ready by Thursday to come back. So then we can carry on. And then, we'll just continue by doing the new material. We'll do the problem sets. We'll do the sample final, and eventually we'll figure out a date. But I think the 9th is very doable for having the final. And again, it is exclusively based on 11 and 12, and then we're done. So after that, well, if you're looking for some more math, you can try stats. They have their own complete course in statistics. And if you really feel ambitious, you can try pre-calculus. That definitely is offered every semester. All right, so I guess hopefully I'll see you all in person. Now I have all the exams. They're actually in the back seat of my car, so I can't forget them. I wanted to hand them out today, but of course I can't. But you can look in Moodle and see what your actual score is, and then I'll bring them with me on Thursday. All right, so if there's no last minute questions, I'll see you all on Thursday.
Thank you.
Okay, you're welcome.
Thank you. Have a good day.
All right, bye.